Hey guys, today we're going to be looking at orbital overlap in the formation of covalent bonds, and we're going to be looking at the idea or the theory of hybridization. Okay, so when we have two atoms and they are going to form a bond, they're going to have their own individual electrons in their own individual orbitals, and as they bond, they're going to have those orbitals overlap with the electrons sharing or occupying the same space. So when two atoms are bonding to each other, their individual electron or electrons in individual orbitals will occupy the same space. So essentially the same energy, right? So this orbital overlap is what gives rise to a covalent bond. So the idea that these atomic orbitals overlap and form a bond. So this is going to be the basis for valence bond theory. Okay. So valence bond theory states that two atoms which have unpaired electrons in their orbitals can overlap to give rise to a chemical bond, a covalent bond. So this covalent bond is formed by the sharing of those electrons between the two atoms during that orbital overlap. So the two electrons themselves have to have opposite spins in order to occupy the same space, just like what we see with a regular atomic orbital. So one has to be spin up and the other spin down. So just like with our atomic orbitals, these will have a spin up and a spin down component. And then the electrons themselves, or the orbitals that are overlapping between those electrons, are going to overlap on what's called the internuclear axis. So the axis where the two orbitals overlap is known as the internuclear axis. So if we have, for instance, two hydrogen atoms, they each have their 1s orbital. They are going to overlap along what's called the internuclear axis. And we'll have those two electrons, one spin up, one spin down. So we'd say that the 1s orbital of one hydrogen is overlapping with the 1s orbital of another hydrogen to give rise to a bond. When we think about bond formation, we think about it as kind of a when we think about bond formation, we think about it as a balance between repulsive and attractive forces. So we've got a lot of charges going on. We've got positive charges from our nucleus, our protons within our nucleus, and we have negative charges from our electrons. The negative charges of the electrons are going to be attracted to the positive charges of the nucleus or the protons. And then electron-electron or proton-proton, those are going to cause repulsion. So when we're thinking about a bond distance, it's going to be a balance between those attractive and repulsive forces. So our bond is a balance between attractive and repulsive forces. We make covalent bonds in order to get an octet for our atoms, right? We're trying to have all the atoms have an octet that want them. So hydrogen, helium, those type of things will not. But the other ones, they want that octet. So we bond in order to get to that octet or in order to fill that outer shell with electrons. So that is one reason why we bond. And of course, like I said, it's that attractive and repulsive forces that are affecting all of that. So if we think about a hydrogen-hydrogen bond, we think about hydrogen-hydrogen distance versus energy. If we are far, far away, if we're infinitely far apart, so our two hydrogen atoms don't feel attractive and repulsive forces, we have an energy value, which is less than 0. Okay? And then as those hydrogen atoms get closer and closer together, that energy goes down. And it'll eventually reach an energy minimum. Okay? And then it will very rapidly increase in energy. So this energy minimum here, this is our bond angle, or sorry, bond distance. So that energy minimum is that energy of that bond, so that when we take our two atoms separated apart, the energy that's released when we combine them together. So this is going to be a value that is going to be dependent upon attractive and repulsive forces. If we get our two nuclei closer together, there's going to be such great nuclear repulsive forces that it's going to rip the atom apart. So any closer, there's too much repulsive forces. Between the nuclei. So proton, proton. So our protons are repelling in this case. Any further, and here we have a lack of that attractive forces between the electrons and the protons, and all you really feel is the repulsive force of the electrons. So not enough attractive forces. Too much repulsion from electron interactions. So it's that happy medium between the two, getting the enough attractive forces while not being too close to be incredibly repulsive. So, the geometries that are seen in our last lecture, those molecular geometries and electron domain geometries, are not really able to be explained without additional theory. So, valence bond theory uses the idea of hybrid orbitals in order to explain how atomic orbital mixing leads to new orbitals and that affects the shape of our molecules themselves. So, valence bond theory, which I'm just going to start calling VB, uses the idea of hybridization to explain the shapes that molecules exhibit in VESPR. Okay, so the idea is that atomic orbitals mix, they form these new hybrid orbitals. And these hybrid orbitals have the correct geometries to account for the bond angles that we see. So our mixing of orbitals, this hybridization, is a mathematical operation that combines the wave functions of the atomic orbitals to determine the end shape of the hybrid orbitals. So our hybridization is basically a mathematical function. So remember our wave functions from when we talked about Schrodinger and quantum mechanics. Okay, so these new hybrid orbitals are going to have different energies. Have different energies from the atomic orbitals. Okay, and we'll look at those. Now, as a note, however many atomic orbitals you mix, you're going to get the same number of hybrid orbitals after hybridization. So, number of atomic orbitals in will equal your number of hybrid orbitals out. Okay, so let's look at the idea of a two orbitals. So if we take two orbitals and we mix them. So this is not, with hybrid orbitals, we're not overlapping orbitals, we're mixing orbitals. So just keep that as a distinction. When we overlap orbitals, we form bonds. When we mix orbitals, we hybridize them. So our first option for hybridization is sp. So with a hybridization of sp, we have one s orbital mixing with one p orbital. And when that occurs, we form two sp orbitals. Okay, so we have an atomic s orbital and atomic p orbital combine or mix or hybridize to form two sp2 orbitals. So they have a weird shape. Their large lobes are 180 degrees from each other. So if we look at them, it looks something like this, and then usually we just write it as this. These are a little bit more spherical in shape than the P. And then this right here would be our center point where our nucleus is at. We see this in BeH2. So here is our Be atom. And then our hydrogen atom. So in this, here are our two sp orbitals overlapping. So this bond is an sp orbital overlapping with an s orbital, and that forms our covalent bond. Same thing here. So both of these have sp orbitals overlapping with s orbitals. And let me just gonna real quick put this Be in the center. Like that. And the electrons are there. Okay. Next, we take 1s plus 2p. So we have an s, 2p. They're mixed. And we get 3 sp2 orbitals. And they are 120 degrees from each other. Didn't specifically say this, but these are 180 degrees. Okay. So, an example of this would be boron trihydride. I'm just writing the little electrons in here. So these bonds are formed by the overlap of an sp2 and an s orbital, like so. Our next one is 1s plus 3p. And 1 plus 3 gives us 4 sp3 orbitals, which are 109.5 degrees. Each of the big lobes are 109.5 degrees away from each other. We see this with something like CH4. Each of these bonds are the overlap between an s orbital and an sp3 orbital. Okay? So, what happens is when we think about our orbitals and what orbitals exist, we think about our 1 s orbital. Then we have 3 p orbitals. So we can combine these to form our bonds. And every time we add them together, we're going to get different characteristics based on how much of the characteristic of the hybrid comes from S, how much comes from P. So we have what's called the P character of the hybrid orbitals. Or we can call it the S character if you so choose. So how characteristic it is of one type of orbital versus the other. So when we have an sp hybrid orbital, we have 50% s character and 50% p character. So remember that our s is spherical and our p is a dumbbell shape. So when we combine them, we get an almost more spherical look to our orbital than the p orbitals are by themselves. As we go from sp to sp2, we've now gone to 33.3% s character and then 67.7%, or sorry, 66.7% p character. So we're getting an elongation of those orbitals because we have greater p character or less s character. And then going into sp3, we're at 25% s character, 75% p character. So they're going to be even less spherical in shape and more elongated. Okay? So when we think about our types of hybrid orbitals, we can kind of combine into a little table where we have atomic orbitals combined, our hybrid orbital set, our geometry, and then we can look at a couple of examples. So we can have an S plus a P that gives us two sp hybrid orbitals, and those lobes will be 180 degrees from each other, like so. And this is a linear geometry. An example of this, BF2, HgCl2, BH2, BEH2, or B2, BH2. Okay, next, an S plus a P gives us three sp2 orbitals. These are 120 degrees from each other. So they form 120-degree bond angles if those lobes are 120 degrees away from each other. So this is going to be our trigonal planar geometry that we see here. Examples are BF3, SO3. And then S plus P plus P plus P gives us four sp3 orbitals, like so, where they're all 109.5 degrees away from each other. So this is our tetrahedral. And this is stuff like CH4, CH4, NH3, and this is stuff like CH4, NH3, H2O, so on and so forth. Okay, you may be asking yourself at this point, well, yeah, but there's other geometries beyond tetrahedral. But we've exhausted all of our orbitals that we've seen so far, right? We've used all of our s orbitals, which there's only one, and then we've used all of our p orbitals. So in order to go and look at our other geometries, our trigonal, bipyramidal, and our octahedral, we're going to have to look at those expanded octets a little differently because they're going to have those p orbitals we talked about. So p orbitals are going to be included in this hybridization, and that'll allow us to have those expanded octets. So atoms in period 3 or below have available d orbitals. Remember that n equals 3 is the first shell where we see those d orbitals. So we have those, and they can be included in this hybridization to get to expanded octets. Okay, so let's look at these. One example of this is PCl5. So PCl5, we have our phosphorus, which has 5 electron groups around it. So that means it's going to need 5 sets of orbitals in order to mix and form hybrids. So we have our S, and then we have our 3 P's, and then we can include 1 D, giving us sp sp3d. And there's 5 of these total, so you get 5 hybrid orbitals. Okay, I'm not even going to attempt to draw that because it gets very, very funky. But what you get with this, so I'm not going to show these, but I'm going to show choop, 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 like that with bond angles of 120 degrees and 90 degrees. So we get those 5 hybrid orbitals that are sp3 hybridized, sp3d hybridized, and we can then make trigonal bipyramidal. So all trigonal bipyramidal atoms or molecules will have a sp3d hybridized central atom. And then, of course, we have octahedral. So octahedral, we have 6 electron groups. So to have 6 electron groups, we have to have 6 orbitals shared or mixed, giving us 6 sp3d2 hybrid orbitals. Okay. So we can figure out our hybridization just by knowing our VSEPR. So if we have our Lewis structure, we can count our electron groups or electron domains, and that will determine our type of hybridization. So if we have, let's look at our number of electron domains. Our hybrid orbitals, and then our geometries. So if we have 2 electron domains around a central point, we need 2 equivalent orbitals. So that's the whole thing. These bonds, we're assuming they're equivalent. So all of the bonding orbitals have to be equivalent in energies, and that's another reason why we hybridize. So we get 2 sp orbitals, and that's going to be a linear geometry. At 3 electron domains, we need 3 equivalent orbitals, so we mix to get 3 sp2 orbitals in a trigonal planar geometry. 4 electron domains, we need 4 equivalent sp3 orbitals, and that'll be our tetrahedral. 5 electron domains, 5 sp3d hybrid orbitals, trigonal bipyramidal. And then last but not least, 6 electron domains gives us 6 sp3d2 hybrid orbitals and octahedral geometry. So just kind of to recap the whole purpose of hybridization. So first let's look at what's going on. In an atom, if you've got an atom, all of the orbitals around it that are bonding with other atoms in a normal bonding method are going to be the same energy, or they need to be the same energy. We can't have one CH bond, the orbital there, having a significantly different energy than another orbital making a CH bond. So we want those orbitals around our atom to have the same energies. Our bonding orbitals. Okay, so all the bonding orbitals for carbon should all have the same energy. All the bonding orbitals around sulfur should all have the same energy, right? So if we're talking about bonding with s orbital versus bonding with p orbital, they're going to have very different energies. So that's one of the reasons why we hybridize, in order to get orbitals with the same energy. We take all the orbitals we're going to bond with, mix them together, and then hybridize them so that they have the same energies. And that's because, like I said, our atomic orbitals all have different energies. We talked about if we have a multi-electron atom, then the s orbitals are going to have different energies than the p orbitals within the same subshell, or within the same shell. That's not true for hydrogen, right? But in the case of a multi-electron atom, we're going to have atomic orbitals that have different energies based on whether they are s orbital, a p orbital, a d orbital. So again, we combine them, hybrid, and then we have orbitals that can bond with the same energy. An additional reason that we need hybridization is because the shape of the atomic orbitals are not representative of the shapes that our molecules make. So they don't match with Vesper. So they're not going to give us the geometries that Vesper says we should have. So these are why we hybridize. Okay, that is everything for this section. Talk to you guys later. Bye.